Assalamu alaikum students. Welcome to another online session for the course Digital Logic Design. My name is Ali Roman and this session is designed for the students of BCS 3A and BCS 3D. In this session we will be continuing the concept of memories here. So first of all, let us see the content we will be discussing in today's session. So let us first see the contents we will be discussing in today's session. Basically, we will be having the introduction to the today's session with the revision of the previous session, what we have learned in the previous session. Then we will be discussing the error detection and correction. What do we mean by error detection in data bits and how we're going to correct the data. And then we'll study the code, Hamming code, how the Hamming code is being generated and what is the application of Hamming code in today's session. As far as the readings and acknowledgements are concerned, we are at chapter number 7 of the book Digital Design with Introduction to Verilog HTL. So before going to the error detection and correction, let us first review what we have studied in our previous session. In our previous session, we have studied about the internal structure and the decoding mechanism of a RAM. Basically, have discussed a static RAM, and we have seen that we use latches in order to store the information there, and we've discussed the basic structure or the basic unit in order to hold a single bit. That is a basic cell. Then we have discussed the interfaces of the basic cell and how we're going to perform read and write operation within the basic cell. And then we have designed a static RAM of 4x4 words. And then we have seen that if you have to design a static RAM of some specific configuration or of some specific capacity, then what are the resources that are required in order to implement that memory. So to start with, our memories basically are used to hold the data or to store the data so that that data can be utilized further for the applications or for the processor in order to process some information or in order to achieve some task. So it is a requirement that the data should be reliable. By the reliability of the data means that whatsoever we have stored should be there and can be retrieved after some passage of time in the same way in which we have stored that data or we have maintained that data. If there is any sort of change in the data or there is any sort of a loss in the data, then we can say that that data is not reliable and that data is faulty or that have some errors. So we do have some error detection and correction schemes. So first of all, let us first see what is the difference between the error detection and correction schemes. The error detection schemes are the schemes that allows us to detect the error in the data, but that don't have any capability to correct that data. Whereas for the error correction schemes, that also detects the data, but also enables us to correct the data as well. So at different levels, in order to maintain the integrity of our data, we use different sorts of error detection and correction schemes. So basically what we are doing here is these schemes basically are used in protecting the occasional errors in storing and retrieving the binary information. So if there is any sort of an error occur in our binary data, these schemes would help us in order to store and retain the information. As far as the parity is concerned, basically parity is a method of the error detection, but the single bit parity cannot correct the data, cannot is not basically used for the correction purpose. It's only used for the detection purpose. So in order to correct the data, we have to use multiple parity bits that are stored within the data word in the memory. So we do have some specific error detection schemes that have only the capability to detect the error, and for error correction schemes that have the capability to detect as well as to correct the errors as well. As far as the detection process is concerned, we can utilize single bit parity, but as far as the correction process is concerned, we have to use multiple parity check bits that are stored within the data inside the memory, so that we can either detect and correct the information bits as well. These sorts of schemes are basically more utilized in the dynamic RAM basically. So let us see how these schemes are implemented, and we will be discussing the Hamming code here. Basically this is the one of the most common used in RAM, was devised by R.W. Hamming, and this coding mechanism is known as the Hamming code. So what do we mean by the Hamming code, and how this code is implemented, and how this code will help us in detect the errors or to correct the errors? So in a Hamming code, let us first see the specification. How many bits are used for the data bits and how many bits are used for the parity bits. Basically what we are doing is we are adding some redundant bits in the data, so that in order to retrieve the data and to see the data is valid or data don't have any sort of error, basically those redundant bits are used. So basically we are using k parity bits here in an n bit word. So the total number of bits are n plus k we used to store. What we are doing here is, in order to maintain the integrity of the data or reliability of the data, we are using some additional bits. Basically we are wasting our storage, but that wastage is ensuring us that in order to retrieve the correct data, we have the capability to do so. But if we don't store some additional bits here without any sort of additional bits, if we store only simply the data bits, there is no way that we can retrieve the data if there is some error or some mistake in a data. Mistake in a sense that some bit is flipped due to some any occasional reason. So in that particular case, the reliability of data is lost. So we are basically compromising on our space, but that is ensuring us to hold the integrity or to reliability of the data. So what we are doing is, if we are storing n bit data word, we are using k bits, k additional bits. So the total data bits we are storing in that particular location are n plus k bits. Now these k bits basically are of specific position in the data. We're going to insert those k bits in specified positions, and how we're going to identify those specified position is that basically those position numbered as, if you see that, numbered as a power of 2 basically are reserved for the parity bit. So if we are storing n bits, we're going to see what are the bit placements or position that are the power of 2. For example, bit placement 1, 2, 4, 8, 16, 32. These are the placements that comes with 2 raised power n notation, or you can say 2 raised power 0 equals 1, 2, 4, 8, 16 and 22. So these are the placements that are reserved for the parity bits, and the remaining are the data bits in the total n plus k bits. And now we'll see how these parity bits are generated and how we're going to compute the parity. Basically we're going to compute the parity and we're going to store that parity with information bit, and then afterwards in order to check if there is any sort of an error we're gonna use some check bits, and that check bits are also computed in the same fashion, and we're gonna compute the even parity or odd parity, and that have some specific results according to even parity or odd parity, in order to decide that we have some error and at which placement we've got some error. So let us first see for the first step how these uh, k parity are generated. So consider this particular example here. We've got a 8-bit data word that is 11000100. So we are adding 4 redundant bits here because we've got 4 placements here that can be represented with 2 raised power n notation with that data bits. So that are P1, P2, P4 and P8, which we can see from these bit positions. This is 2 raised power 0, this is 2 raised power 1, this is 2 raised power 2, and this is 2 raised power 3. Let me write it also. This is 2 raised power 0, this is 2 raised power 1, this is 2 raised power 2, and this is 2 raised power 3. Those placement in that information basically reserves are reserved for the parity bits. So we're going to compute this parity. How we're going to compute this parity here? So instead of storing the 8-bit data, we are storing 12 bits here that contains 8 data bits and 4 parity bits. P1 is basically the exclusive OR of the bit placement of 3, 5, 7, 9 and 11. So we're going to retrieve those bits and we're going to construct the exclusive OR gate in order to decide the state of P1. So this is basically, if you see that in that particular case, that is this 3, bit placement number 3, bit placement number 5, bit placement number 7, 9 and 11. So at bit placement 3 we've got 1, then we've got 1 at bit placement 5, then we've got 0 at bit placement 7, 0 at 9 and 0 at 11. We're gonna compute the exclusive OR operation here basically to decide P1. So this is 1 exclusive OR 1, exclusive OR 0, exclusive OR 0, exclusive OR 0, that is equal to 0. So P1 is set to 0 in this particular case for that data. Now coming to P2, P2 is basically the exclusive OR operation between bit placement 3, 6, 7, 10 and 11. So we're going to compute the exclusive OR at the bit placement number 3 for computation of P2. 6, 7, 10 and 11, that is 1, exclusive OR 0, exclusive OR 0, exclusive OR 1, exclusive OR 0, that is equal to 0. Similar is the case for P4. We're going to pick up the bits at placement number 5, 6, 7 and 12, that is placement number 5, 6, 7 and 12, and their result is 1. And P8 is computed as the exclusive OR of the bits at placement 9, 10, 11 and 12, that is 1. So these are the bits that are additionally stored with the data bits. So let us see what would be the data that would be stored. So that is 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 0. This is P1. If you remember, this is P2, this is P4 and this is P8, which we have computed earlier. Now how we're going to see that if any sort of error occurs here or not. First of all, we're going to see what are the checker bits that are required. So when we have to read from the memory, the parity is checked over the same combination of bits including the parity bit. So the parity has been computed including those parity bits that is basically checked here. So C1 is basically the exclusive OR of bits 3, 5, 7, 9 and 11, and C2 is basically 3, 6, 7, 10 and 11, and C4 is 5, 6, 7 and 12, and C8 is 9, 10, 11, 12 in the same way in which we have computed or we have assigned the parity bits. So we're going to compute that again as the exclusive OR operation. So how we're going to detect the error? Basically, if we see that a zero check bit designate an even parity. If a check bit has a value 0, it represents an even parity over the check bits, and a 1 designate the odd parity. So since the bits stored with even parity, the result is C1, C2, C4, C8 equals 0, 0, 0, 0. Basically, if we are storing the number with even parity, basically we are computing the number of ones that are being stored in the number, and their quantity should be even. And if we are exclusive or performing the exclusive OR operation of these respective checker bits with the parity bits, and the result is 0, 0, 0, 0, which indicates that there is no error that has been occurred. So if basically these placement, this 4-bit code basically tells us that if there is an error, and also tells us the position at which position the bits are flipped basically. So if C is not equal to 0, we have some number in place of C here, that is a 4-bit number. That 4-bit binary number formed by these check bits give the position of the erroneous bits, that specific placement in which the bit is flipped basically. So let us see the examples here, that in case if we don't have any error, and in that case if we have an error, how these checker bits will help us to identify the placement of that specific error. So if you see that these are the bit placement of a 12-bit data, that 12-bit data contains 8-bit data bits and 4-bit parity bits. And if we see that there is no error, then C1, C2 and C4 and C8 if we compute, C1, C2, C4 and C8 if we compute that, that is basically 0. By the same way we've computed parity bits. So for no error, C1 will be equal to 0, C2 is equivalent to 0, C4 is equivalent to 0 and C8 is equivalent to 0. So what we are doing, we can also check in the same way that we can construct the exclusive OR operation between the parity bits and the checker bits, and because both are having the same relationship for the exclusive OR operation, and if the bit placements are same, then the result of exclusive OR is 0, and if there is the flipping, in any case the parity bits are changed. If in any case, then in that particular case we're going to identify that bit placement contains the error. So if you see that the error in bit 1, for example, in this particular case, this bit is been flipped from 0 to 1, the remaining bits are same. So in that particular case, C1, C2, C4 and C8 has a value 0, 0, 0, 1, and this indicates that the bit placement 1 basically is erroneous, and basically is flipped, so its previous value is 0. Now this is the way we are going to detect the error in that particular placement. Now if the result of the C1, C2, C4 and C8 is 0, 1, 0, 1, which means that the bit placement at fifth placement, basically that is this bit is flipped, or is the one that contains the error. So with these checker bits we are able to identify the exact placement which is containing the error. So here we can detect a single bit error, and also we can identify the placement that is used to detect the single bit error. Now let us conclude our discussion by some facts here for the Hamming code. The Hamming code can be used for the data words of any length, and for any length, basically how many number of bits that are required for the checker bit or the parity bit, that is dependent upon that number has the bit placement, so that satisfies 2 raised to power n notation. So the total bits in a Hamming code is n plus k bits, which we have already discussed, and the value c basically that consists of k bits and has a range 2 raised to power k value between 0 to 2 raised to power k minus 1, and the range of k must be equal to or greater than n plus k, giving us the relationship of 2 raised to power k minus 1 must be greater than or equal to n plus k. So if we have the 3 number of checker bits, this is table 7.2 basically represents so the range of data bits is basically 2 to 4. If we've got 4 checker bits, that the range is 5 till 11. If we have 5 checker bits, we have 12 to 26, and if we have 6 checker bits, so check bits, we have 27 to 57, and if you've got 7 check bits, then the range of the data bits is 58 to 120. Well, student, this was all for today's session. Basically, we've got the introduction to the Hamming code here that is used for the error detection process here, and basically that is being utilized in a RAM in order to identify the error, and so that we can correct it and we can revive our data, and we can eliminate any errors that are occurring in the data. And we've seen that the Hamming code is being constructed in such a way that we are adding some redundant bits at some specific placements. That is basically the placement in the data that satisfies 2 raised to power n notation, and we've said that we are computing those parity bits in a fashion that we are constructing some exclusive OR operation between some specified bits in order to compute those parity bits, and we are storing those parity bits with the data bits. Then what we are doing is that we are computing the check bits in the same way, in a way in which we have computed the parity bits, and If the check bits results all 0, which means that we don't have any sort of an error, and it results 0 in that particular case if we are using the even parity. So if the check bits have some number that basically specified that specific placement which contains the error bit. So till now students, I hope so the concept is clear. We will meet again in our next session, in which we will be discussing the read-only memories and PLAs and PALs, and we'll see how we're going to implement some Boolean functions by using read-only memories and programmable logic arrays, or using programmable array logics.